Greetings 1314. So this is 5.1 combining functions. So in this section, we're going to combine functions through the basic four operations of arithmetic: addition, subtraction, multiplication, and division. And so we're going to do the basic four operations, and then we're also going to do something called compositions of functions in here. And we're going to compose one function within another function with the composition. And so with combining functions, we've already talked about what functions are. So you're going to take two functions, and you're going to combine those with the basic operations, and you're going to make something called like a third function. And so you're going to create a new function from two existing functions, basically. And so I think the best thing to do is maybe jump into this first example and give you something to grab onto to know what I'm talking about. So if a driver attempts to stop while traveling at X miles per hour on dry level pavement, the reaction distance is R of X equals 11th x, and the braking distance is B of X equals 1/11th x squared, where both distances are in feet. So the part A says write a formula for a function S in terms of R of X and B of X that gives the stopping distance when driving X miles per hour, and evaluate S of 55. I know that's a lot of words, but here's S of X is what they want. And so X is the miles per hour, or the speed that you're going. And then the function is going to calculate distance. And so this is sort of like you're driving down the road and you see a rabbit, and the first thing that happens is it takes your brain a few seconds to realize, oh crud, there's a rabbit in front of me. And so this is going to be the speed that you're going. This is going to give you the distance that it takes your brain to say, oh crud. And then this is going to give you the distance after your brain actually says that and hits the brake. This is going to give you the physical distance that the brake actually takes to stop. And so if we want the full stopping distance, well, that's like the crud distance, which is R of X. If you think about it, we're going to add those two distances to get the total stopping distance. So this says R of X, a little bit. That's R of X plus B of X. So we can say S of X is equal to R of X plus B of X. Or we can do what we know about the function. So R of X is 11th x, this looks like 1/11th x squared. And if we want to know S of 55, we'll look at our S of X function. It looks like 11th times 55 plus 1/11th. And if we do that, I believe we should be getting 121 and 275. First one's giving me 1, that second one's giving me 275. And that gives me a total distance of, I believe, 396. And we're talking about feet here. So just to recap, if we're driving 55 miles per hour, it's going to take us 396 feet to stop. You might notice this 121 is coming from this R of X part. So it's going to take us 121 feet just for the reaction. And this thing you might notice is coming from the braking part. And that 275 is going to come from braking, hitting the brake. Okay. So similar down here, these are the same three functions. We have R, B, and S. Can I get a little closer, a little less blurry maybe? So we want to look at these graphs. I think the easiest to identify might be the R. So that's a first order. That should be the linear one. This is my R. The next one is my B, looks like 1/11th x squared. You might notice that as just a regular parabola. We're just, what is that, a stretch? I believe we're stretching it just a little bit, but it looks like a normal parabola, so it should be this one that's going through the vertex on the axis. Not changing the vertex at all. And so that's my B, and so you can probably guess this last one here, this green one, that to be my S. And then you might ask, well, how are we attaining S from B and R? Well, if we look at the graph, where X is 20, and this is close to 40, this is 40. So we add 40 and 40, it's going to be about 80. And so I guess long story short is that we're adding the y values here, right? And so if we're adding the functions, we're adding the function values. And so if we're talking about function values, we're talking about y values that we're talking about. And should be it. Okay. So this is coming from the previous function, r of x, b of x, and s of x. So I'm hoping you know how to plug things into a function at this point. So for, what is it, r of x is 11/5 times x. So hopefully you can crunch some of these, but we're just plugging into the function that we have. So this one should be 24.2. This one should be 48.4. This one should be 72.6. This one is 96.8. This one is 121. Now we're going to the other function that looks like 1/11 x squared. So we do 1/11 x squared. That's 2/11. 1 and 5. This one is 99. The next one is 176. This is the 275. Right here, 121 plus 275. This is the 396. So this right here, or this column here, is the same thing that we did on the previous page. We're plugging 55 into our function. What is that looking like? Let's get a little closer, maybe. And so hopefully you notice a pattern here. If we're adding this and this to get to this, well, we can do the same thing here. 2 here, 48.4 plus that should be what, 92.4? 92.4. 171.6. 272. Okay. So I think what we're doing, just to recap a little bit, we're talking about the basic first operation that we can talk about. We're talking about addition. And so we're going to add two functions to create a new function. So we're adding r of x and b of x to create s of x. And so the book really likes to give you things in different formats. So they give you the problem in a verbal format. The part A, we did things symbolically. Part B, we did things graphically. Part C, we did things numerically. And so they really kind of expounded on their 4 different formats there that the book likes to give. And so a quick thing on notation is what this next thing is about. We have a few definitions here. So if f of x and g of x both exist, the sum, difference, product, and quotient of two functions f and g are defined by the following. And so quick word of advice, if you see this thing on the left, you're almost never going to evaluate this thing. You should always write out this definition over here that's on the right. So if you see the thing on the left, don't do that. Do the thing on the right. Write out your definitions. Like you might have to commit this to memory. So we need to fix that. Okay. With that said, so I know we gave it the definition was x's, and now they're going to throw in numbers. So we have f of x equals 4x minus x to the third, and g of x looks like x plus 3. So if I see something like f plus g of a minus 1, first thing I said is we'll write it out. And so you might notice with these definitions, when we have a single x that looks like this x value is going to get used twice in each of these. We're going to use this -1. We're going to use it twice. And I'm telling you this kind of preemptively, because when we do compositions of functions, we're only going to use that x quantity once. And so here we're going to use it twice. F plus g of minus 1 looks like f of minus 1 plus g of minus 1. And that's coming from the definition right above here. And so f of minus 1, we can figure out f of minus 1. We're plugging in a minus 1 to our f function. So that looks like 4 times a minus 1. Minus a minus 1 to the third. So that's my f part of that function. I'm going to add that to my g part of the function, which looks like a minus 1 plus 3. I believe this side is giving me a minus 4. I have a minus 1 to the third is going to give me minus 1. And I'm subtracting another minus 1. That's a minus 4 plus 1 on that side, I believe. And adding that to 3 minus 1 gives me 2. Minus 4 plus 1 gives me minus 3. And then plus 2, I believe overall this is just trying to basic order of operations at this point. So crunching some arithmetic, this should give you a minus 1. Okay. So we're going to evaluate these things, and I believe we're going to evaluate these things symbolically first. You can probably guess it. We're going to do things graphically, numerically. Okay. Go through all the different forms. Excuse me. So g minus f of 0 is g of 0 minus f of 0. Now, if I see this, I know my g of 0 looks like something that looks like 0 plus 3. I'm plugging 0 into my g function. I'm subtracting that, and I might want to take note at this point, like I'm always putting parentheses around this function, right? And this might come in handy, because you notice we're doing subtraction, and we might have to do some distribution. 0 plus 3 minus f of 0 looks like 4 times 0 minus 0 to the third. And I might have spoke too soon because this is just what? 3 minus 0 here. 3 minus 0 should give you the next thing is g times f of 2. And so we're doing g times f of 2. Times f of 2 is g of 2. We're going to multiply that by f of 2. Okay. So g of 2 looks like 2 plus 3. We're going to multiply this by f of 2. So f of 2 looks like 4 times 2 minus 2 to the third. And so this side is giving me 5. I'm going to multiply this by 4 times 2 is 8. 2 to the third is 8. You might notice that's giving me a 0. This is going to be 5 times 0. This should be 0 overall. And the last one, I think I got just enough room. You might notice these are the same numbers, so you might be able to use that fact to your advantage. But if we're doing f divided by g of 2, this is f of 2. We're dividing that by g of 2. So if we look at f of 2 is coming from this side. We're going to get 8 minus 8. We're going to get that 0 on top. We're going to get 0 over G of 2 was what was giving us the 5. And if we look at this, this is like the pizza and people problem. We have no pizza and we have 5 people. Guess how many slices each person's going to get? This is okay to do. This is 0 over 5. We can divide 0 by any number. That's fine. And as I promised you, we got it graphically now. So we have a graph. Let's see if I can zoom out a little bit. If that's any better or worse. It's hard to see those numbers. F plus G over minus 1. So still the same approach that we're doing. We don't want to do this. We want to do F of a minus 1. And we want to add that to G of minus 1. Now the main difference here is we're not plugging these into a symbolic function. We're using a graph to get the values. So F of a minus 1, the red thing is the F. I look here at minus 1. So this one's really easy to read on the graph because this is the Y value of 0. So we're doing 0 plus. I look at my G value where it's a minus 1. And this looks like it's coming through right here at 3. So this is 0 plus 3 is going to give me 3. Okay. So G minus F of 0 looks like G of 0 minus F of, we're talking about where the X is 0, what is my G value? And so if I look back up here where my X is 0, that's this thing. My G is the blue one, it is at 2, minus my F value at 0 is 1. So this looks like 2 minus 1, you probably guessed already. Drop my coffee. Move this a little bit. Okay. And the next one, for G times F of 2, and you'll probably guess this already from here, right? The definition of G of 2 times F of 2. And now looking at my function for where my X value is 2, I believe my G value here. If you wanted to stop here, you could. Well, that's what I do. F of 2, my X value is 2, my F value up here is at 3. So 0 times 3, you probably guessed it, 0. That's divided by G of 2. So we've already found these functions. This is F of 2 over G of 2. And so my F of 2 was a 3. My G of 2 was 0. And now you think about this, can we have F of 2 or 3 divided by 0? F of 2 divided by G of 2 is going to give us 3 divided by 0. And we think about this, we have 0 in the denominator. This is the first way plus 1 divided by 0. This is the thing. Undefined. Okay. And we had things symbolically, we had things numerically. Or look, we had things symbolically, we had things graphically, you could probably guess. We're going to do things numerically now. So now the big difference, we're not plugging things into a formula, we're not looking at a graph, we're looking at a table, basically. But we're still doing the same thing. We still write these definitions. Plus G of minus 1. We can guess this by this point, F of minus 1. Now we're looking at the table, make sure you know your F function for your F value. But F of minus 1 is 4, G of minus 1 is 2. I believe 4 plus 2 is still 6. Part 2, we're doing g minus f of 0. So g minus f of 0 we're going to minus f of 0. And so you might want to make sure you get these in the right order. G of 0 is going to give me 0. F of 0 is going to give me 1. And if I do 0 minus 1, it's giving me a negative 1. G of 2, G times F of 2 is G of 2 times F of 2. And now I'm picking out values from my table. G of 2 is this one. At 2, it's going to give me 1. And I'm multiplying that by F of 2 at F at 2 is going to give me 3. 1 times 3 is going to give me 3. Now I'm doing F divided by G of 2. So that's F of 2 divided by G of 2. So F of 2 is going to give me, G of 2 is going to give me 1. 3 over 1 is just 3. Okay. Okay, so we're taking two functions, and they're kind of like your parent functions. So if you want to go out on a Saturday night, and one of your parents is telling you, yeah, you can go out, and then your other one says, no, you can't, the overall story is you're probably not going to get out. So this, I want to like describe as kind of the strict parent rule. And so your function is as strict as the strictest parent, is the best way to describe it. And so we want to think about restrictions on the domain. So if we look at our f of x function, which is x squared plus 1, you might notice this is a parabola. And so if we draw a parabola, it's going to go all the way left, all the way right. And so if we think about the domain of this thing, it's going to be all the real numbers. From minus infinity to infinity. And so there's no restrictions on f. But g of x, if we look at g of x, we have a square root there. And so then my question is, what can we not plug into a square root? So we can't have negative numbers. Can we have 0? Square root is 0, 0, 0 is okay. So we can have anything that is 0 or above. If we want to do 0 or above, we do 0. There's two different ways we can kind of write that. Okay, so I'm going to do part A and C kind of together. So part C, ask you to write an expression for each of these things. So I want to write the expression, and I want to talk a little bit about the domain. So the domain for each of these is going to have at least this restriction. It's going to be at least this strict. Okay, so if I look at the first thing, f plus of x is f of x plus g of x. And if I look at my f of x, that looks like x squared plus 1. And I'm going to add that to square root of x minus 1. You might notice a few of these terms simplify, but if we do this, this is going to give me x squared. I'm going to have a plus 1, and I'm going to have a minus 1. That's going to simplify that to 0. And then we're going to have a plus square root of x. So this is my f plus g of x function. And I could write it out over here the way that they have it in the problem. This is that one, right? The f plus g of x. go. So we have this, and I want to talk about the domain. So in this one, it's obvious, but it may not be here. So whether this is here or not, this is going to give us the same restriction of x is greater than or equal to 0. But even if this somehow the square root simplified out, we would still have this restriction. This makes it obvious that we still have the restriction because it's still there. So if I look at f minus g, I'm doing f of x minus g of x. And this is where the parentheses are really common. You have x squared plus 1. And then we subtract square root of x minus 1. I'll probably do this in a little weird order. I'm going to do it in descending, make it sure it's in descending order. So I'm going to do x squared. I'm going to do a minus root x. And if I come back to this one, I have 1, and I have a minus 1 makes this actually a plus 1. So this should be a plus 2. And if I want to know this guy's domain, it's the same thing. X has to be greater than or equal to 0. Move on. The third one is f of x times g of x. I don't want to do a whole lot with this because this is x squared plus 1. Root x minus 1. I guess a little bit maybe. I'm doing x squared root x minus x squared plus the root x. Not the prettiest thing, but I guess I can do it. Minus 1. And the domain on this side is still going to be the same. So x has to be greater than or equal to 0. Okay. And let me get the last one right over here. And I'm bringing it up to the so f divided by g of x is f of x divided by g of x. My f of x looks like x squared plus 1. This thing looks like a square root of x minus 1. And the domain, so this is part of the domain, you might notice. But now when we use the operation of division, we actually introduce a new thing. This is as a denominator now, and there's something about denominators. This is going to have an additional restriction from the previous ones. In division, you always have to check the denominator. So x minus 1, we do not want this thing to equal 0 on the bottom. So what makes this thing equal 0 on the bottom is our question. So that's when the root x is equal to 1, or when x is equal to 1. So x, recap, x cannot be 1. So we have x is greater than or equal to 0, and x cannot be 1. So that's one way you could potentially write it. Another way is an interval for going from 0 up to 1, but we do not include the 1 we skip right over the 1 and come on the other side of it and finish off to infinity. Okay. And we have all these written, so let's look at this next problem. It should make it a little quicker. But if we do f plus g of 5, we know f plus g is this x squared plus root x. So f plus g of 5 is plugging 5 into this thing. So 5 squared plus root 5. 5 plus root 5. This is a simple way to give it in the book. F minus g of 1. What happens when we plug 1 into this thing? So that's going to give me 1 squared minus the square root of 1 plus 2. I believe that's like what? 1 minus 1 plus 2? Give me 2. F times g 0. Yeah, I might just go with this form. So if we do 0 squared plus 1, and root 0 and minus 1, you might notice this is just 1 times a minus 1. Minus 1. Okay, and then the last one is f divided by g of 3. And so if we're looking at this, f divided by g, we're doing this x squared plus 1 over root x minus 1, we're plugging 3 in. F divided by g of 3, 3 squared plus 1 minus 1. This is 3 squared gives me 9 plus 1. Minus 1 still there. Combine that to 10. Okay. So this is kind of a quick recap of the thing that we just talked about. So the domains of the sum, difference, and product, they're all going to be as strict as the strictest functions. So they're going to inherit all the restrictions from their parents. The other thing is that when we have a quotient, when we start to divide things, we have to check that our denominator is not equal to 0. And so that could make another restriction that you have to check. Example 4. So trying to throw more words at you. So the expenses for a band to produce the master soundtrack for an album include renting a music studio and hiring a music engineer. These fixed costs are $500 and the cost to produce each album with packaging is $450. Assume no other expenses. Find a function C that outputs the cost of producing the master soundtrack plus X albums. Find the cost of making the master track and 3,000 albums. Okay, so this is something that you should have an understanding from. We're doing a linear sort of problem here. We have a fixed cost and then we have a cost per album. And so we want a cost function of x, represent that. And we have this 450. So 4.5, and this is per album. So the word per, I'm hoping that's going to be slope. That's our slope. That's the thing that's attached to our x. So this is per album, and this is going to be the number of albums. And we're going to add the 500 base cost to that. And so this is a basic linear function that we've talked about before. And so we have C of x. And now we want to find out what's going to cost to make, what, 3,000 albums? So 3,000 is the x value. So we're just going to plug 3,000 into the function and just figure it out. And that should give me what? 13,500 plus 500. I believe overall this is going to give me 14,000. The next one says, suppose each album is sold for $9. Find a function R that computes the revenue from selling X albums. Okay. And then find the revenue from selling 3,000 albums. So we want to find a function for the revenue. If we're making $9 per album, X albums, that's going to be 9 times X. And so that's going to be our revenue function. And so hopefully this is making sense. Sell 0 albums, we're going to make $0. We sell 1, we're going to make 9, 2, 18, and so on, right? Okay, so that's our R of X function. R of 3,000. We're going to figure out for 3,000 albums. So 9 times 3,000 is the computation we do. I believe that's going to give us 27,000. And so maybe a little bit of overview of like what's happening here. If you're running a business, it's going to cost you money to run that business. You're going to sell stuff, you're going to make revenue, and then if I want to talk about the net money that I'm making, that would be the profit that I'm making. So profit is going to be your revenue, how much money you're taking in, minus how much money you're paying. Okay, so profit, and you're maybe heard this before, but profit, or P of X, is going to be your revenue minus your cost. And so there's a few ways we could figure this out, and I think they're trying to make it point home. P of X, we can look at it as these two functions. We can look at P of X as being R of X is the 9x. We want to subtract 4.5x, so this is where parentheses really handy. If you don't have parentheses, we do the 9 minus 4.5 is going to give us 4.5x. If you don't have the parentheses, you might miss this being minus 500, right? Okay. And so if we want to find P of 3,000, we can plug 3,000 into this. 4.5 times 3,000 minus 500. We could do that. That's one way to do it. The other way is you recognize it's revenue minus cost. We're doing the same number here. 3,000. 27 minus 14 is going to give you 15,000 profit. So there's a few ways to work at it. This one. And so now we're going to kind of lead into the next concept about the composition of functions. And so these first two I'm hoping are g of x is 3 times x minus 1 squared plus 1. We're going to throw 2 in there. So we're throwing 2 in place of the x. The g of 2 looks like 3 instead of x. Now I write 2 minus 1 squared plus 1. 3, 2 minus 1 gives me 1 squared plus 1. This is 3 plus 1. I believe this is giving me overall 4 if I crunch these numbers. Okay. Now g of k, if this is g of x, now k is taken in the place of x. So g of k looks like 3 times k minus 1 squared plus 1. So I guess if I wanted to, I could do some foiling or something here. I don't really have to. This is descriptive in itself. That's actually what vertex form for a parabola. But there's no way to like crunch this to a number. I'm hoping you realize. There's always going to be this variable k in there. Okay. So what happens if we plug in instead of an x, we plug in an x squared, so g of x is x minus 1 squared plus 1. Now if I want to do g of x squared, throwing in an x squared everywhere that there's an x. Okay. Now, I'm going to write my g of x function again. 3x minus 1 squared, and I'm going to plus 1. Now, instead of g of x, I want to do g of x plus 2. And so this looks like 3. And now instead of x, I want to write, and this is where you should really use your parentheses. X plus 2. And then I want to subtract 1 squared. And so just to kind of reemphasize, this x is now becoming an x plus 2. This x is taking this x's spot. I still need the minus 1 and squared here, right? Don't start dropping symbols at this point. Plus 1. So if you get this part of it, I think this is the main part. There's a little bit of cleaning up I can do with this. 3 with x plus 2 minus 1 becomes x plus 1. Plus 1. I'm going to do this a little quickly, but you should really write this out twice. It's a square. Because if you don't write it out twice, x squared, you might miss this little 2x in here. And so I'm going to distribute this a little bit. This is 3x squared plus 6x plus 3 plus 1. This gives me 3x squared plus 6x plus 4. Let's simplify this a little bit. And you might have that question, well, what the heck are we doing? Why are we doing this? And the quick response is because this is going to lead us right into compositions of functions. And so if I wanted to create another function, think about a different function, like f of x being the x plus 2, the thing that I plugged in there. This is like I'm plugging my f function into my g function. And so this is like plugging a function into a function, which is going to be compositions of functions. And so we'll talk a little bit more about that next time. And technically, I could have done it with this one up here as well, right? Because x squared is itself. So I could think about that as being a different function too. We can do this with compositions of functions. All right. So I'll see y'all next time, I guess.